Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe. All right, lecture 24 is an introduction to algebra. We're going to start the lecture off with a student perspective on what to expect from algebra, with a little bit of background. So let me let him come on up and take over for a minute.
Hello, I'm Robert Ward, and I'll give you a brief presentation and talk on my experiences in algebra. All right, I'll start off by telling you what to expect. You're gonna have to get used to using a lot of symbols in math and rearranging or manipulating equations, or graphing, which is taking an equation and making it into a, I guess, an image of what it's doing. You probably don't know about it yet, but you'll eventually know what I'm talking about. You may have already learned some pre-algebra, like order of operations or something like this. And you're probably moving on to elementary algebra, or at least pretty soon. So that's what I'm talking about, manipulating equations, graphing, that's all in elementary algebra. And, well, it'll start pretty easy, but you will have to get used to using the symbols, and it'll be pretty weird. But once you understand the basic ideas, have a good grasp of what you're doing, it'll move pretty smoothly for a while. Eventually it will get a bit more complicated, but it won't be too bad, and for now you don't have much to worry about. Anyway, I'll give you a brief talk on the history of algebra, how it came to be what it is now. The father of algebra was a Persian man named Al-Khwarizmi, who was a mathematician, a scholar, and I believe an astronomer. He founded algebra by making a systematic, logical method for solving linear and quadratic equations. He combined Greek geometry with Indian arithmetic and Hindu-Arabic numerals, and used concepts like Algebra, I believe it's how it's said, which is basically the restoration or completion of something, restoring something or something like that. He used this to simplify equations and showed equations through diagrams, images, like the graphs I was talking about earlier. Probably a bit different, but something similar. This laid the groundwork for algebra as it's known today. Of course, this was developed over many years, but that was the start of it. Now I'll tell you about some places where algebra is used in careers or just regular life. It's used in fields like engineering, business, science, and is sometimes used in daily life in things like finance or home improvement. It's used in some areas like that. It varies a lot. All right, as a final note on my experience in algebra and some recommendations, it will take a little bit of time to get used to the symbols and the strange equations, which you probably have no experience with, or very little. But if you understand the basic concepts and keep that in mind, then it should be relatively easy for a while. It will eventually get a bit more complicated, but if you stay grounded in your basic concepts and keep a big picture, then it should be, well, it will be complicated, but it should flow pretty smoothly. But you don't have to worry about that for a while. For now, it's going to be pretty easy, as long as you get used to everything, which isn't too much. That's all I have for you.
Okay, thank you. Okay, so let me get into some details on this. So Al-Khwarizmi's book on algebra, you would kind of expect that it probably had things that looked like this in it. But you'd be wrong. the symbolic nature of algebra wasn't added until later. Instead, the way that this would have been worded would be something like the following. 2 roots and 1 amount to 5. And then it would have been solved with sentences something like this. Subtract the 1 from the 5, there remain 4. Divide the 4 into 2 parts, and each part is the root. So that is what algebra would have looked like in its original book by Al-Khwarizmi. The modern symbolic nature of algebra was added a bit later. Francois Vieta and René Descartes were the primary contributors in that regard. And that's, late 1500s, early 1600s. So when I think of algebra, let me tell you what I think of. I think of algebraic expressions. And so there are actually several algebraic expressions, and I'll just briefly go over them. We won't go into detail on but a few later. There are algebraic phrases, which I'll just denote as phrases. And they are things like this, 2x plus 1. It's an algebraic phrase. There are equalities, or equations sometimes they're called. We'll just call them equations. And they would say things like 2x plus 1 equals 5. There are also inequalities. X is greater than 5. There are identities, like a plus b squared is equal to a squared plus 2ab plus b squared. There are functions, typically functions you get into in what's usually called Algebra 2, but they are basically just input-output machines, and it's really just a rule that assigns one output to every input. So I could write that as a rule that assigns one output for one input. They're denoted like this. F of x equals x plus 1. That says for every input x, there's one output. So if x is 0, 0 plus 1 is 1, the output is 1. If x is 1, the input is 1, the output is 1 plus 1 or 2. Just for example, the square root of x would not be a function, because if I give you an input like, say, 4, the square root of 4, of course, is 2, but it could also be minus 2, because minus 2 times minus 2 is 4. So there would be 2 outputs, potentially. Typically, if you want to use the square root as a function, what we end up doing is just taking one part of it, either the negative or the positive root. There are relations, algebraic relations, and these take various forms. But for example, a table of values, x and y, 0, 1, 1, 2, 2, 3. Some pairing of values just relates the variable x to the variable y. And finally, something you've probably already seen, I know you've seen it before, are formulas. Things like a equals pi r squared. That's the area of a circle. Pi is the transcendental number, 3.14, etc., etc. R is the radius of the circle. So you input the radius of the circle, multiply, you square it, multiply it times pi, and you get the area of the circle. So that's a formula. So algebra is the study of relationships between quantities using symbols to describe, analyze, and solve problems involving unknowns and patterns. I think that's as good a description of what algebra is as you can get. And there are many. Oftentimes, though, it's best to relate it to, something more concrete. So let me give you the kind of problem that you might have that where algebra could play a role. So let's consider the lemonade stand problem. So let's say that you spent $10 buying supplies to set up a lemonade stand. So I'm just going to write that our cost was $10. And we bought enough supplies to produce, we'll call it N for number, 20 glasses of lemonade. That's what our $10 bought us. And so the question is, what kind of profit can we expect? How do we figure out what our profit is going to be? Well, that's going to depend on the cost, or the price that we set for each glass of lemonade. Because the revenue, that's a business term for money that we make by selling an item. Our revenue is equal to the number of units that we sell times this unknown quantity, x, the cost that we have not yet determined. So x is the cost. So that is our challenge, is to figure out that's not the right term. Price. So x is the price that we charge for each glass of lemonade. If we know that price and we sell all 20 of our glasses, then we can determine how much revenue we've earned, how much money we took in. And so the fundamental algebraic relationship is that the profit will be equal to the revenue minus the cost. That just makes sense, right? So let's say that we made $21 in selling our lemonade, and we spent $10 buying the supplies for it. How much money did we make? Well, it's 21 minus 10. We made $11, you see? So we'll actually return to this problem later in the lecture and solve it. Okay? But first, let's talk a little bit more about the details of algebraic expressions, in particular about variables. So you'll oftentimes hear people talk about equations and call them algebraic sentences. Yeah, you may have heard that before. And the idea there is that it is a complete thought. And in writing, we learn that sentences, right, they usually have, who remembers the things that sentences has? They begin with a capital letter, they end with an end mark, they have a subject, a predicate, and they express a complete thought, right? Well, if it doesn't have all of those, maybe it just has, say, a subject. You know, Happy Bob. Then this is not a sentence, it's just a phrase. Or if you just had a predicate, riding the train. That's a phrase. So similarly, when we don't have an equality or an inequality sign written, we can call an algebraic expression an algebraic phrase. And so here's an example. 2x plus 1. That's an algebraic phrase. Now what is this x? What are these things, these variables? Okay? Usually, at least when you start algebra, you'll have two variable types. And we usually label them x and y. And we usually call x the independent variable and y the dependent variable. So x is usually called the independent variable and y the dependent variable. I hope I spelled independent and dependent right. So what does it mean to be an independent variable and a dependent variable? Well, this is the way to think about it. The independent variable is the variable that you choose the value of. It's your choice. So for example, in the lemonade problem, the cost, or say the price that we're going to sell each glass of lemonade for, that's in our control. We can set that price. That's the independent variable. The profit, that's the dependent variable. It's going to depend on what choice we made for the independent variable, you see? So we choose an independent variable, and a consequence of that is that determines the value for the dependent variable. A good example of that is hours worked versus money earned. Okay, so assuming that you make some amount of money per hour, let's call it $1 per hour. If you work for 10 hours, you have earned $10. It was your choice to work the 10 hours. That's the independent variable. And as a consequence of that, you earned that $10. You see? Does that make sense? But don't let variables bother you because they behave exactly like numbers. So let me explain that. Let me just write variables behave. I don't know how to spell behave. Is that right? Does anyone know if that's right? Oh, no I? Okay, so just behave like numbers. So x plus x is just equal to 2x. Think of x as an apple. If I have one apple and I add it to another apple, how many apples do I have? I have 2 apples. So when you see x, you can think apples. 1 apple plus 1 apple is 2 apples. Now here, notice that the x looks a lot like our multiplication symbol, doesn't it? So when writing algebraic expressions, we don't use the multiplication symbol that looks like an X to indicate multiplication. Instead, we use a dot or nothing at all. So there are two ways to write x times x. You can write it like this, x dot x, or you can write it like x. Now, me personally, if I write the same variable multiplied times itself like that, I would put a dot there. If it was a different variable, x times y, I would leave the dot out. I just write xy, okay? So when you put two variables next to each other, it's understood that they're multiplying one another, okay? This, though, either way, it's equal to x squared, because that's what squaring means. When you multiply something times itself, that's a square. If I do it, multiply something by times itself 3 times, x times x times x, that would be x cubed, you see? Usually we like to simplify the algebraic expressions that we get, and we do that by collecting like terms. This like terms is something you'll hear a lot in kind of the algebra community. I don't really feel one way or another about it, but I'm used to it, and so I say it. I'll say collect like terms. But what does that mean? Well, let's do an example. If I wrote down the expression x plus y, there's really nothing we can do here. X and y are not like terms. They are different terms. This is one, the variable x, and this is the variable y. However, if I had 3x plus y minus x, I could simplify this. Because here's 3 x's, or apples, and then here at the end of the expression I have another x that's to be subtracted. Yeah? So 3 apples minus 1 apple, 2 apples. So I can rewrite this expression, or simplify it, as 2x plus y. And so that's what we mean by collecting like terms. We bring them together and we simplify them by adding, subtracting, multiplying, dividing, whatever needs to be done. So here's a slightly more complicated version. So when I write my z's, I put a little line in the middle so you know it's a z and not a 2. So let's simplify this expression. We've got 7x cubed times y to the 5th times z squared, all divided by 49x squared y to the 4th. So we'll break this up into little pieces. The number part, the 7 over 49, well, that's just 7 over 7 times 7. One of those 7s is going to cancel, so we're going to get 1 over 7 for that part. Then we have the x's. We've got x cubed divided by x squared. Well, that's just, remember the rules of exponents, x cubed minus 2. So x to the 3 minus 2 power, right? That's how we work with exponents, because we've got a cubic exponent in the numerator. We have a square in the denominator. They're like terms, so we can combine them. Y to the 5th divided by y to the 4th, well, that's just times y to the 5 minus 4. And finally, there's nothing to do with z. It's all by itself, so we just have times z squared. And so if we evaluate those exponents, we'll get 1 over 7 times x, y, z squared. Okay? Does that make sense? Exactly as if it was numbers, right? So x cubed over x squared is the same thing as 3 cubed over 3 squared, which is just 3, right? Using our rules for exponents. Let me give you one to try. Now, so simplify 3x squared plus 4x cubed times 1 over x. So pause the video, come back when you have your answer. Okay, so we can write this expression. Nothing we can do with 3x squared yet, so we'll just rewrite that. But 4x cubed times 1 over x, that's the same thing as 4x cubed divided by x, which is just 4 times x to the 3 minus 1 power. Again, rule of exponents, 3 minus 1 is 2. So that gives me 3x squared plus 4x squared. Now you see that these two terms are like terms, and we can just add them as usual. So x squared is still apples. So we still have, because they're like terms, we just call them apples. So 3 apples plus 4 apples is apples. 7 apples. So 7x squared is the final answer. Okay? Here I'd like you to try another. The quantity, the square root of x squared times y cubed times x divided by y plus 4x squared y squared. So go ahead and pause the video, try that at home, come back when you have your answer. So I've intentionally tried to make it as much stuff to do as possible. These are ridiculous looking expressions, and I don't know that you'd ever encounter any like this in real life, but let's just proceed anyways. So there's a couple of ways that we could approach this. We could recognize immediately that the square root of a squared number is just a number, right? So the square root of x squared is just x. But let's just go ahead and just use our rules of exponents, okay? So I'm going to go ahead and write the square root of x squared using our rules for exponents. So that's going to be x squared to the 1/2 power. Well, that means we're going to multiply the exponent 2 times a half. So times 1/2. And when I'm going to go ahead and move this x right next to it, that's x to the 1, so that means we add 1 to that. So that's x to the 2 times a half plus 1. And then I have times the y cubed, but we have a y in the denominator, so that's an exponent of -1, so that's y to the 3 minus 1. And then there's nothing to do on the far expression, 4x squared y squared. Let's go ahead and simplify this. Well, 2 times a half, well, that's just 1. And 1 plus 1 is 2, so that means this is x squared. And then y to the 3 minus 1, well, that's just y squared, plus 4x squared y squared. Now you see that these two terms are like terms, and so we can just simply add them. So now our apples are x squared y squared. Okay, so I have 1 apple plus 4 apples, you see? 1 apple plus 4 apples? 5 apples. So 5x squared y squared. And another. Okay, go ahead and simplify the expression x cubed times y plus 2x cubed times y squared. Come back, pause the video, come back when you have your answer. Well, there's no exponent manipulation to do, so you can see clearly that we do not have like terms, do we? So is there anything at all that we can do to this expression? Well, we've talked about it before, but let me remind you about the distributive property. This says that if I have some number a times b plus c times the quantity b plus c, so we usually set that off with parentheses. We think order of operations, the parentheses are telling us that we must first add b and c before we multiply it with a, right? But we can distribute the a inside the parentheses as follows. A times the quantity b plus c is equal to a times b plus a times c. You see that? Well, if we look at our expression we have here, right, we see that we have an x cubed and an x cubed in both terms in the expression, right? We also have a single y. We have a y here and we have a y here. Now, it looks like y squared. I understand that. But y squared is just y times y, you see? So they both, at least, both terms of the expression have one y in them, yes? So we can factor that out, as we say, and we'll write it like this. We can get the x cubed out, and we can get 1y out. So that's our a. And what's left behind? Well, x cubed y, there's nothing left behind there. So we have 1 plus 2, which we did not factor out, and a y. See that? So if you use the distributive property rule on x cubed y times the quantity 1 plus 2y, then you will get back the original expression. And in some way, this is simplified. Depends on what you're doing, on whether that's going to be something useful to do or not, but it is a legitimate manipulation of the algebraic expression. Okay? I want to move on to looking at the algebraic relationships that are expressed in tables. Okay, so here is a table of values. And again, remember, we usually, when we write x, y like this, we're thinking x as the independent variable, the one that we choose, and y as the dependent variable. Okay, so let's look at the table. Can you figure out what the relationship between x and y is? Do you see what's going on there? A lot of times what helps is to rewrite the column in the dependent variable, and I'll rewrite it in a different color so we see that this is not just part of the table, by simply writing in the original independent variable value x in a way that it gives you as a total the values on the right in the dependent variable. So we could write this as 0 plus 1. That would give us 1 for y, yes? And then we move to the next one, next row. X equals 1. We see that y is equal to 2. So let's go ahead and write our x in, 1. And what do we have to do to that to make it into 2? Well, we could add 1 to it. See? Now let's look at the third row. X is 2, y is 3. So let's first write the x value, 2. Now all I need to do is add 1, and I get 3, you see? Now if the rule that when you write these rules in, as I'm doing here, they have to be the same for each row. You can't change it from row to row. That would not be a legitimate use of this method, okay? So you can see here the next one will be 3 plus 1, 4 plus 1, and the kind of natural extension of this is to simply say, if this is x and this is y, that y is equal to x plus 1. You see? See how I got that from this table of values? Yeah? Yes? And so what I've ended up with is what we'll talk about next, equations. See? Let me give you one to try. So I want you to analyze this table of values. We have x the same as before, 0 through 4, but y is giving us values of 0, 2, 4, 6, and 8. And try to, in the end, extract an equation that expresses the dependent variable in terms of the independent variable. So pause the video, come back when you have that done. Well, again, we can do what we did before. We want to rewrite the dependent variable column in terms of the independent variable. So I'm going to go ahead and put in my independent variable value of 0 for the first row. But that is actually equal. That is actually equal to the dependent value. So I'm not sure that I have anything useful yet. Let's do it with the second one. Here we have 1. And we have to turn that into 2. Now we could go the route that we did before and do plus 1, and maybe we'll just do that. But we remember that all the rows have to be the same rule. And if I add 1 to this, then I have to add 1 to the previous row, in which case this would be the wrong y value. It'd be 1 instead of 0, right? So what if instead I said, you know what, let me just do this. What if I multiply the value 2 times the independent value 1? That'll give me 2, and I can do it up here as well. 2 times 0 is still 0, yes? So it looks like I may have a rule here. Let's try it in the next row. Write in the independent value 2, do our rule, 2 times 2, that is 4. It looks like it's working. Let's do it for the fourth row. X is 3, so we'll take 3 and we'll multiply 2 times it. 2 times 3 is 6, so it looks like we have a match here. Finally, 2 times 4 is 8, and so our rule that we've come up with is that for a given x value, the y value is equal to 2 times the x value. And that's the equation y equals 2x. Okay? Before we talk about equations, though, I want to talk about evaluating algebraic expressions. And this is pretty straightforward, and you probably already figured this out, but I'll just go through it anyways. So let's start with a really easy example. Let's start with a formula. We know that the area of a rectangle is equal to its length times its width, where I've represented length with a cursive L and I've represented width with a W. Now if I were to say, hey, I've got this rectangle and it's 2 units, its length is 2 units, so L equals 2, and its width is 3 units. Width equals 3. We know how to use the area formula for a rectangle by plugging these numbers in and doing the arithmetic, yes? So what is the area equal to? Can someone tell me? It's 2 times 3.
6.
It's equal to 6. So we've calculated the area by using a formula, yes? Let's go back to our favorite equation we had at the beginning, y equals 2x plus 1. If x is equal to 1, what is y equal to? Well, y is equal to, all we have to do is replace in the phrase 2x plus 1, the x with the value 1. So y is equal to 2 times 1 plus 1. Well, 2 times 1 is just 2, and 2 plus 1 is 3. What if x is equal to 2? Well, then y would be equal to 2 times 2 plus 1. 2 times 2 is 4, plus 1 is 5. Make sense? Yeah?
Yes.
Pretty straightforward, right? That's why I almost didn't put this in but it's important to at least just say that this is how we evaluate algebraic expressions, by replacing the variable, the independent variable, with the numbers of our choosing, you see? Okay, I would like you to try one. We'd like you to evaluate y equals 3/2 x minus 1 for the value x equals 2. So go ahead and pause the video, come back when you have your answer. Okay, so if x is equal to 2, that means that y is equal to 3/2 times 2 minus 1. Well, 3/2 times 2 simplifies because we have a 2 in the numerator and a 2 in the denominator. And so that just leaves us with 3. And 3 minus 1 is equal to 2. Okay? Understand? Okay. And finally, we can get to algebraic equations, right, which everyone thinks of when they think of algebra. Equations. Such a scary word, right? Just means that we have an algebraic phrase and another algebraic phrase, and we connect them with an equal sign, okay? But I do want to point out there's something I like to call the rule of equations. I'm going to try to write this in as 10 Commandments-y style as I can. What is done to one side must be done to the other. Exclamation point. Does that make sense? So whatever you do on one side of the equation, you have to do that on the other side as well. And this is actually how we solve a lot of algebraic equations. Have you ever heard anyone say solve an algebraic equation before? Yeah? All right, so here we have an algebraic equation. 2y minus 3 minus 4x equals 5. And we want to solve for y. What does that mean? That means that we want to get y on one side of the equation and nothing else, and everything else on the other side of the equation. So I can say that y equals, and then some answer, you see? That's what we mean by solve for y. As it sounds now, all we have is have we solved for 5? I'm not sure. That doesn't seem logical. But so how do we do this? Well, we're going to use our rule of equations. Maybe you could call it the golden rule of equations. That seems more symmetrical with biblical passages. What is done to one side must be done to the other. It's a little bit like the golden rule. But anyways, so golden rule, I'm going to call it that. The golden rule of equations. Golden rule of equations. So let's apply here. What do we need to do? Well, we want to get y all by itself. And so the game that you play is you try to move everything from this side to that side. It's a little bit like that puzzle game you play where you try to move tiles around to get the tile out. So you have to like move things out of the way, and yeah. So first thing we might consider doing is collecting like terms, because we see that we have a number and a number, but they're just on different sides of the equation. So if I were to move this minus 3, move this 3 over to the other side with a 5, then we could, combine the like terms and simplify. So let's do that first. So to get rid of that 3, I need to add 3, because if I add 3 to the left side, minus 3 plus 3 is minus 3 plus 3? Nope. What is 3 minus 3?
0.
What's the difference between 3 minus 3 and minus 3 plus 3? There's none. It's the same thing. So I want to add 3. That's what I'm doing here. So if I add 3, then I'll get 2y. Adding 3 to the left side just gets rid of the 3. And so we have 2y minus 4x equals. Now I have to add 3 to the right side, though, because the golden rule of equations tells us that what we do to one side, we have to do to the other. Since I added 3 to the left-hand side, I got to add it to the right-hand side. And 5 plus 3 is 8. Yes?
Yes.
Now, next thing, now I've made some progress. It's looking simpler. But I want to get y all by itself on the left-hand side, let's say. It doesn't matter which side you put it on, but let's say we're going to go for the left-hand side. That means we need to get the x on the other side. So we've got this minus 4x thing here, right? And again, these are just like numbers. If you have trouble with it, just imagine that x is equal to 1, and so you have a minus 4. How do you get rid of a minus 4? Well, you add 4. But 4 times 1, right? We're going to add. So we're going to add 4x plus 4x. That's what we're going to do in this step. Adding 4x to the left-hand side just leaves us with 2 times y. But since we added it on the left-hand side, we have to do it also on the right-hand side, and so we get 4x plus 8. Yes? All right, it looks like we're almost there. We have solved for 2y, but we need to solve for y. So how do we get rid of that 2 in front of the y? By the way, the numbers in front of variables are oftentimes referred to as coefficients. So if you hear that term, that's what they mean. That's the number in front of a variable. Okay? So in this case, 2 is the coefficient in the expression 2y. All right? Well, we can get rid of the 2 by simply dividing the left-hand side by 2. So let's divide by 2. If I do that on the left, 2y gets turned into just y. And if I do that on the right, I get 4x plus 8 divided by 2. The whole thing divided by 2, right? Now I can, of course, do that one piece at a time, right? I can rewrite that as 4x over 2 plus 8 over 2. And that will simplify considerably because 4 over 2 is just 2. So that's 2x plus, and then 8 divided by 2 is just 4. So 2x plus 4. And so finally we arrive at, and we could even factor out a 2 out of these, right? We could rewrite that as 2 times x plus 2 if we wanted to. Yes? So in the end, we've simplified this and solved for y and found that y is equal to 2 times x plus 2, quantity x plus 2. That's usually how we say it. We have parentheses, we'll say the quantity. So I would read this as y equals 2 times the quantity x plus 2, where the quantity means what you're about to hear is in parentheses, you see? Okay. Was that terrible? That's some basic algebra right there. Okay? Not so bad, right? I shouldn't have erased the golden rule of equations, but that's fine. I think it's easy to remember, yes? All right, so new equation, 2y, let's say the quantity 2y minus 3x divided by 2 is equal to 1. And I would like you to solve for y. So go ahead and pause the video. Try that now. Come back when you have your answer. Okay. Well, the first thing that we might do is get rid of this 2 in the denominator here. And that's easy enough. We can just multiply both sides by 2. So I'll put times 2 for my first operation. That means if I multiply the left by 2, it just gets rid of that 2 in the denominator. So I'm left with 2y minus 3x. And on the right-hand side, using the golden rule of equations, 1 times 2 is just 2. So I get a 2 on the right-hand side. What do you want to do next, you think? We're solving for y. What do you think we ought to move next? No hiding under desks. Should we divide by 2? Should we add 3x? What should we do? That's really our only two choices, right? We can divide by 2 to get rid of that coefficient of 2 in front of the y, or we can add 3x to get rid of that x on the left-hand side. Because it's a game we're playing. We're trying to move things around so that we get y all by itself on one side. All right?
By 2?
Well, we could, yes, but why not do an easier thing first? Let's just get rid of the 3x, yeah? So let's add, well, fine. You know what? Let's just do what you say. Let's just divide by 2. Why not? Dividing both sides by 2 gives us y minus 3 over 2 x equals, and then we divide the left-hand side, assuming the right-hand side by 2 also. The 2 divided by 2 is just 1, and so we're left with 1. Yeah. So notice, though, when I divided by 2 on the left, I have to divide both terms by 2. Okay? Don't forget that. It's just like with numbers, right? And then now we're left with no choice but add the x and move the x over. So we will do plus 3/2 x on both sides of the equation. Doing it on the left side just gets rid of the 3/2 x, and we're left with just y. And on the right-hand side, we get plus 3/2 x. We'll write it as 3/2 x plus 1. And thus we've solved for y. Yeah. Let me put one more problem for you to try in that kind of puts everything in at once. Everything that we've had so far anyways. So this will be another solve for y problem though. Yeah. So here we have the equation x squared y minus xy squared plus yx equals minus x squared y. Would like you to solve for y. So pause the video. Try that now at home. Come back when you have your answer. So the first thing I notice when I look at this is that we have a y in every term. Do you see that? You may also notice that we have an x in every term. Yes? So if I think the first thing I'd like to do is I'd like to divide both the left and right side, because if I do it on the left, I got to do it on the right, by x times y. And see if that doesn't make it look a little bit nicer. Does that make sense? Yeah. So dividing the first term by xy just leaves me with x, because I had x squared times y. If you divide that by xy, you're left with just x. The second term leaves me with just a y. Yes? And the third term, well, yx divided by xy. Is that the same thing? Is that just equal to 1? Let's look at it for just a second. I have yx divided by xy. Well, these variables represent numbers, and numbers commute. Right? That means that x times y is the same thing as y times x. So I can just rewrite it if I like. Y times x. And if I have the same thing in the numerator as in the denominator, what's that equal to? What is 5 over 5? Or 9 over 9? Or 3 cats over 3 cats? It's 1, yeah. Exactly. So dividing yx by xy leaves me with just the term plus 1. But I got to do it on the right-hand side too. So that'll give me a negative x, and that's all that's left, because x squared y divided by xy is just x. Yes? Yeah? Okay. Now, I think what I want to do next is move the y to the right-hand side, because it doesn't matter. I know that you're used to thinking that y equals something is y on the left and everything else on the right, but the side doesn't matter. So I'm going to move this y over to the other side by adding y. So I'll do plus y. Got to do it on both sides, though. If I do it on the left-hand side, I'm left with just x plus 1. And on the right-hand side, I get y minus x. Yes? Make sense? Now, I want to get y all by itself over here on the right, so I'm going to add x. So let's do plus x. Doing it on the left-hand side, I'll get x plus 1. What is that? X plus x. What is x plus x? What is x plus x? What is 1 apple plus 1 apple? 2. So 2x. Yes? 2x plus 1 on the left. And on the right, I'm just left with y, because minus x plus x is 0, so I just get y as what I'm just left with y. And so this equation says that y is equal to 2x plus 1. Even though the y is on the right-hand side, it doesn't matter. It's fine. You can read it from right to left. That's okay. Y equals 2x plus 1. Or if you want, y equals 1 plus 2x. Okay? All right. Let's return to the lemonade problem and finish that up. So our basic expression was that profit equals revenue minus cost. Pretty sound logic, yes? Profit is our dependent variable. That's the thing we would like to determine. Or maybe we want to choose that as, no, that's fine. It's our dependent variable, so we're going to call that y. Okay? And revenue, you might remember, is equal to the number of items that you sell times the price that you sell them at, where price is the thing we're trying to figure out, because we don't know what to set the price at yet. The number of units we have to sell, though, is just 20, so I'm going to go put 20 in as a coefficient on the independent variable x, where x is the price of a glass of lemonade. That's how much we charge when we sell 1 glass of lemonade. And then minus cost, you remember that the cost was $10. We spent $10 to buy the supplies for this lemonade stand. So we have the equation y equals 20x minus 10. Okay? Now, there are a few things that we could do to analyze this lemonade problem. We could, for example, make a table of values. X, y equals 20x minus 10. Oftentimes it's a good idea to write the equation for y in its column in a table. That way you can compute it on the fly. So let's say, where do we start with price? We just need to choose some sample values to consider. Okay? So we could, for example, say, well, let's give it away for free. That's where I charge $0. Yes? And all I need to do to figure out what y is, what's my profit if I give it away? I mean, you can kind of guess what the profit's going to be, right? But 20 times 0 is 0. We just substitute it in. I'll write it like this. 20 times 0 minus 10 equals, well, 0 minus 10 is just equal to minus 10. that means that I've lost $10. You see? And that's, of course, what we knew would happen if we give away our lemonade. What if we set the price to be half a dollar? That's 50 cents, right? Well, in that case, we plug in for x the value 1/2. So that's 20 times 1/2 minus 10. Well, 20 times 1/2, that's just 20 divided by 2. That's 10, right? So 10 minus 10 is 0. That's 0 profit. We could call that the break-even price. Break even. Where we took in exactly what we paid out. Okay? We didn't make any money, but we didn't lose any either. What about $1 as the price for a glass of lemonade? Well, to figure out what the profit would be for that, we just simply go in here and we plug in x equals 1. So that's 20 times 1 minus 10, and that equals 20 minus 10, which is $10. So there we have a profit of $10. If we were to choose $2 for a glass of lemonade, we would have 20 times 2 minus 10. Well, 20 times 2 is 40. 40 minus 10 is 30. Now, if we wanted to, remember what we talked about graphing in a previous lesson. Yes? We could express the values in this table with a graph. So here's my x-axis. Here is my y-axis. So we usually choose the independent variable to be the horizontal axis. Okay? And we choose the dependent variable to be the vertical axis. So I can draw in some points for this. X equals 0, we got that y was equal to minus 10. So I'll go down here, I'll call this minus 10. That looks terrible. Let's try that again. Minus 10. There's that point there, x equals 0. When x was equal to 1/2, we'll say that this is 1, and well, actually let's space it a little better than that. Call this 1, and call this 2. So that's 1, 2. So 1/2 would be right about here. And when we have 1/2, y is equal to 0. So that's right here on the x-axis. Yes? And what about when x is 1, we get that y is 10. So that's here. Here's 10. When x is 1, y is 10. Put that point right there. And when x is 2, that's $2 a glass, y is 20. Excuse me, 30. That's way up there. It's too far off. We can't even draw it. But you can see we could draw in. We see these 3 points are collinear. That means they lie on the same line. And in algebra, you will study the equations of lines in some detail. Right? That'll be like the first thing you really study in depth, the equations of lines. And what we can do with such a thing is we can use it to extrapolate. Right? We can look at it and say, well, what if I charge, a little bit more than 1? It's going to be a little bit more than 10, you see? So you can kind of guess what the y value is going to be given an x value just by following this line. Yeah? So we can see visually, right, that this is our break-even point because y is our profit, remember? And we want profit being greater than 0 is what we mean by profit, yes? So you can visually see where the break-even is just by looking at this graph, okay? Now you might have wanted to do something like this. Maybe you had a profit goal. So we want the profit to be equal to $5. Maybe we were doing this lemonade stand because we needed to buy something for a school project or pay for something in a school project, raise money for, the cheerleader squad, whatever, right? And so we had this target value. We need to raise $5. So that means we need to make $5. So if I set my profit equal to $5, I'm just going to call it 5. How can we use this equation to figure out what we need to set the price to? To make a profit of $5, what does the price of a glass of lemonade need to be? Well, we're going to solve for x. Okay? So I say, all right, well, that means if y is equal to 5, that means that 5 is equal to 20x minus 10. And to solve for x, what do? We play that game again, right? We got to move everything to one side or the other. Since x is already on the right side, let's just leave it there. Now let's add 10 to both sides. So we'll do plus 10. Adding 10 to the left-hand side, 5 plus 10 is 15. Adding 10 to the right-hand side just gets rid of that minus 10. So we get 20x. Now we're almost there. All we have to do now is get rid of that coefficient of 20. So let's divide both sides by 20. Dividing the left by 20 gives us 15 divided by 20. And on the right-hand side, we're just left with x. And so now we know what the price should be. 15 over 20. That's not the nicest looking expression, is it? Remember that 15 is 5 times 3. And 20 is 5 times 4. Yeah? The 5 in the numerator cancels the 5 in the denominator. And we are left with 3/4. So we need to charge 3/4 of a dollar. That's 75 cents a glass if we want to make our profit of $5. Yeah? Does that make sense? So that is 75. How do we write cents? Like that, I think? Something? I don't know. 75 cents. So that is a very, very simple example of using the kind of algebraic reasoning that you will learn when you go through a full course on algebra. So this is just an introduction to it because that is the next logical step in your mathematics education after this course on the fundamentals of mathematics, which is now drawn to a close. This is the last lecture. There's nothing more to say about it. All right. Yeah, thanks for that. That means you enjoyed it a lot. Is that right? Yeah. Yeah, so the next logical place to move on to after this is to study algebra. And this is just kind of an introduction to that, to get a feel for what you're in store for. It's going to draw upon a lot of the basic mathematics that we learned in fundamentals of mathematics. Addition, arithmetic in general, right? It's just something you got to be good at in order to work with it. The rules for exponents will be particularly useful. I don't know what that means, but okay. I guess that means wrap it up. It's getting late, yes. So I really enjoyed teaching fundamentals of mathematics. I hope you enjoyed it too. And look for, in the near future, a course on algebra. Algebra 1, Algebra 2 probably. Thank you. That's all.